So, thank you very much. Thank you to Professor Kato for the invitation to come here. It's always a great delight to be in Kyoto, especially in this room. I like to be in this room, so it's nice to be back. I want to talk about, I hope it will be a gentle talk, an easy talk, nothing too stressful. I just want to make an introduction to, well, just a piece, part of the work of Alain Connes, on what's called noncommutative geometry. Which is a subject which is, I suppose, almost 40 years old. And so I just want to talk about a little piece of this, and it mostly has to do with partial differential operators. I mean, not the whole subject, but the part that I'm going to discuss has to do with partial differential operators from the point of view of Hilbert space and operators on Hilbert space, and especially algebras of operators on Hilbert space. In other words, operator algebras. I should say at the beginning that this subject would not exist without the influence and the work of Gennady Kasparov. And although my lecture and his will be on slightly different subjects, perhaps you can think of my lecture as an introduction to Professor Kasparov's lecture in the afternoon. Certainly everyone in operator algebras was very much influenced by Professor Kasparov, and what I'm going to discuss reflects that. Okay. And as I promised in the title, I want to talk, at least at the beginning, about integral operators. So there will be some background material, several different topics in background material. Maybe we'll call this number one. So I want to discuss integral operators, the famous theorem of Hilbert that you all learn. You learn Hilbert's theorem in functional analysis class. And it has to do with operators like this. There will be some space, some geometric space throughout the lecture, and it will be, for simplicity, a smooth and compact manifold, some decent space. I mean, at various points it could be much more general, but let's assume it's something like this. Anyway, the operators we're interested in are integral operators, like that. And the subject, the theory of these operators, depends very much on the behavior of K. And at the beginning, people investigated continuous functions. And a little later, it was decided that it would be okay if the function was just a square integrable function, like this. And a little later still, still in the time of Hilbert, a further generalization was found to be the best. So there's a way of characterizing this type of operator plus a few more, and that's the condition of compactness. So what I'm really going to talk about has to do with so-called compact operators on Hilbert space, but these are the main examples. And so these were analyzed first by Hilbert, and what he observed right away is that if you have two such operators, T1 and T2, and if you compose them, then the kernel is this function k associated to t is easily obtained from the functions associated to t1 and t2 by a sort of convolution like this. Maybe I'll call this z. I'm sorry. It looks nicer. And so by definition, this is such an expression as this. And what Hilbert observed at the very beginning is that this formula resembles matrix multiplication. In matrix multiplication, you take the ijth entry of a matrix and you multiply against the jk element of a matrix, and then you add up over all j's, and you get the ikth element of the product, like that. So Hilbert was inspired by in this case, algebras of matrices to prove the following theorem. So this is the famous theorem of Hilbert, which tells you how these operators behave in the case when T is self-adjoint like this. So in the language of these kernels, self-adjoint means that the adjoint kernel is equal to k itself, and k star of xy is just k of yx. But like you see in matrices, the ij entry of the adjoint of a matrix is the complex conjugate of the ji entry. Anyway, if you have a matrix like this, then there's some orthonormal basis, ortho of the Hilbert space, consisting of eigenvectors, just like there is in matrices, eigenvectors or eigenfunctions. Like that. And the eigenvalues, for what it's worth, the eigenvalues form a sequence converging to zero like this. This is the famous theorem of Hilbert. And these compact operators that I'm talking about here are precisely, in the self-adjoint world, precisely the operators for which the conclusion is true. And so we'll talk about self-adjoint operators as well as integral operators. So this is a famous result from more than 100 years ago, an ancient result with many beautiful applications to Dirichlet problem, to compact groups, to many other things. And the basic aim is to add some geometry or maybe differential topology to this story. And then we'll see what we get. And this is what Connes succeeded in doing, and what I want to tell you about. Okay, good. So, let me change topics for a moment and give some different background. Suppose D is some sort of linear partial differential operator on the manifold M. For example, some type of Cauchy-Riemann operator, maybe a Laplace operator, something like that. When you study linear differential operators, the first invariant of the operator, which tells you the most about the operator, is the so-called principal symbol, which is a function. You take the operator and you make it into a function. So if D is maybe some expression like this. Maybe the operator has order q. Maybe in local coordinates, we could write the operator in this way. Then this principal symbol here, sigma, is a function of two sets of variables. So one set of variables is are just the points on M, and then at least locally, these xi's are just vectors like this. So, of course, such an expression depends on choosing some local coordinates like this. And then what you're supposed to do to define the principal symbol is you're supposed to forget about all of the terms of lower order, keep only the terms of top order, and then keep the coefficients. And get rid of the derivatives and replace each derivative, each ddx, you replace it by some linear function, xi, of the new variable xi. So d to the alpha, for example, ddx1, ddx2 gets replaced by xi1 times xi2, like this. Just for small technical reasons, it's best to multiply by the square root of -1, no big deal. And so that's the principal symbol. So this is some local recipe to construct a function from an operator As it stands, it depends on a choice of coordinates, but as you probably already know, there's an invariant way of understanding what this is, and it's as a function on the cotangent vector bundle. This function, and this is the reason for the square root of -1, this function will be real valued, not all the time, but if D is, as they say, formally self-adjoint, which means for L2 inner products, one has some formula like this. Oopsie. So the first thing to say about this function is that there's some invariant way of thinking about it. It's a function on something a little geometrical, on the cotangent vector bundle. Incidentally, it's not going to be so important, but you can check that this thing is invariantly defined on the cotangent bundle just by giving a formula for it, which is something like this. The first thing you do is you take D, you take a function on the manifold, and you look at the commutator of D with F. That is, you look at the commutator of operators. F means the operator of multiplication by F, and D means D, and so you can form DF minus FD. It's an operator. And okay, it's some new operator. If D has order Q, this thing has order Q minus 1. But you can do it again. Now it has order Q minus 2. And you can just keep doing it Q times. And after you've done it Q times, the thing on the right-hand side is a differential operator of order 0. In other words, it's multiplication by a function. So this converts a one form, a covector, into a function, or if you like, a covector into a value of a function. That's what this symbol is. So this is not terribly important, but just to emphasize the point that this is a geometric object defined on the cotangent bundle, let me just give you that formula. Okay. And we're going to be interested, did I write it up here? I guess I didn't. Oh, I did. Elliptic operators. We're going to be interested in elliptic operators. Let me assume that throughout I'll be in this world of self-adjoint operators. By definition, D is elliptic if this function I just defined is a proper function. It means that the inverse image of each compact set is compact. So it means, so it's a function, where is it? Yeah, function into R. And as you travel to infinity in this geometric space, as xi gets bigger and bigger and bigger, so the value of sigma on xi has to get bigger and bigger and bigger. Okay, so at one extreme, the 0 operator is not elliptic because this function is identically 0. doesn't go to infinity at all. All right, very good. And do I want to say this now? Let me think about whether I should. Let me just leave this for a moment. Say something else instead. Of course, it's very famous that elliptic operators have many beautiful analytic properties which resemble the properties of harmonic functions or analytic functions. Let me just summarize maybe by saying they have beautiful regularity properties. This is not a real definition, just an idea. So for example, if you try and solve the equation du equal to v, where v is a smooth function, then it's a fact that the only solutions to this equation, even among distributions, are also smooth. So these are very particular operators. They have this important regularity property. If you want to solve this equation in smooth functions, the only place to look for solutions is in smooth functions. Okay. Same also for analytic. Okay, and this is very important in index theory. It tells you that the kernel of this operator, the kernel of an elliptic operator, has to be finite dimensional. Also, the co-kernel is always finite dimensional, thanks to this property here. Okay, one more background. Number one, and number two, number three. Which is an effort to connect number one and number two. And so this is work. Again, all of these things very old. This is some important ideas that were worked out by von Neumann. If you want to analyze an operator, one of these partial differential operators, if you want to analyze it from the point of view of Hilbert space and spectral theory, like we see here in Hilbert's theorem. So this differential operator is certainly not a compact operator. It's not even a bounded operator. It's not well defined as an operator on the Hilbert space L2. And so it's a little complicated to understand how to make a spectral theorem like this for such an operator, but this is what von Neumann worked out. And let me in a slightly funny way tell you what von Neumann worked out. Let me call it just for this talk von Neumann symbol, since we have symbols up here. So what is this thing? Maybe I'll write it like this. It's a homomorphism of algebras, so a morphism of, in fact, Banach algebras, C-star algebras. C-star algebra is a type of Banach algebra. Banach algebra is a type of algebra with topology. Anyway, I'll tell you what this is in a moment. And over here, I'm looking at the algebra of bounded linear operators on the Hilbert space L2 of n. So this thing is notation that the C-star algebraists use. This is the algebra of continuous complex valued. I'm supposed to say valued functions on the space R with one other property, namely they vanish at infinity. As you go to infinity, the function gets smaller and smaller and smaller. One needs one of these symbols. What is the property of this? The property is that if you take these standard so-called resolvent functions, they're mapped by this symbol homomorphism to the corresponding resolvent operators. So for an operator to be good for spectral theory, to have a chance to have a spectral theorem, something like this, the operator must have the property that these resolvent operators are well defined. They have bounded inverses, just like you see. And once you have these bounded inverses, in fact, they can be combined into such a morphism of algebras like this. So the symbol in this case is a slightly funny object. It's a morphism of algebras. Here it's a function. Down here some morphism of algebras. And the reason I call it a symbol is that we can go back to this thing up here. Supposing that D is a partial differential operator, it has a principal symbol. If D is elliptic, the symbol which I defined here, thanks to the fact that it's a proper function, can equally well be thought of in the following way. Principal, oops, yeah, that's right. As a morphism of algebras like this, from the functions on R to the functions on the cotangent bundle. Because if I have a function on R, I can just compose it with this version of the symbol that I defined up here, and now it's a function on T star of M. And this operation sends functions which vanish at infinity to functions which vanish at infinity. If D is elliptic, thanks to this fact here, thanks to this properties here, the definition. And in the case of elliptic operators, thanks to regularity, you can say a little bit more about this von Neumann symbol. Namely, it's a morphism not just from functions on R into bounded operators, but functions into what are called compact operators, exactly these compact operators of Hilbert. So now it's an interesting situation. These two symbols, the symbol from partial differential equations and the symbol from operator theory, now they look the same. Almost the same. They're both morphisms of C-star algebras like this. So is there more than... so superficially, on the surface, these look very similar. On the surface, this looks very similar to this. And so now I ask, is there more going on? Is this just a coincidence that they look the same? Is there more than a superficial connection, relation between the two, between these things? Okay. Of course, the answer is yes, otherwise there would be no subject. So I want to spend a lot of time now trying to connect this object, which is the usual symbol that you learn about in partial differential equations, with this object, which is a somewhat disguised version of these ideas that you see from Hilbert's theorem. Maybe I should say one more thing. I wonder if it's possible to... maybe I'll just stick it down here. So in the world where D is elliptic, just to emphasize, make this funny definition maybe a little less funny. If I take a function here and I convert it into an operator, you can ask, what does this operator do? Well, it's a fact that for elliptic operators, the operator D has one of these orthonormal bases of eigenfunctions, which is up here. And the way this fellow acts on a eigenfunction, it's a little unfortunate. Every function is called f. This fj is supposed to be a function on the manifold M, and this little f is supposed to be a function on the line. I should have used some different letter, but anyway, let me just persevere. This is f of lambda j times fj. So f is in C0 of R. And the fj's are eigenfunctions for this unbounded operator. Thanks to all of the theory behind me, thanks to the work of Hilbert, it can be shown that for this operator there is an orthonormal basis of eigenfunctions, because in the range of this map there are many compact self-adjoint operators. Thanks to that, there is an orthonormal basis of eigenfunctions, and this strange symbol that I'm describing is just doing this thing here. Not so strange. Okay. So far, so good? Any questions? Okay. So I want to describe a beautiful construction of Alain Connes, which interpolates between this construction and this one, puts these two constructions in a smooth one-parameter family. That's the main goal. And the main technique is to observe that this algebra that we see up here can be easily generalized to construct many, many interesting new algebras. This discussion here resembles very strongly matrix algebras, but we can easily change this to get much more complicated algebras than matrix algebras. Maybe I should say new. So first of all, just to place everything in context, as for old, I just mean the fact that if I have a continuous function on m times n, two continuous functions, then on this space of functions there is a convolution multiplication, namely the one which you see up here. So this space of functions, this linear space of continuous functions on m times m, it's an algebra. And now I will show you lots of new algebras by giving examples. So suppose I have, for simplicity, a Lie group. And suppose it acts smoothly on some closed manifold M, like we were discussing. And so there's an action map like that. This action map tells you everything about the action, of course. And so does this space here. Let me call it G semi-direct product M. As you'll see, it's really just a disguised version of G times M. I want to look at all triples like this. And I put in X, but it's not really there. X is just G times Y. So X is determined by G and Y. I didn't need to put it in. So this, of course, this space is isomorphic to just G times M that we started with. But when I write the space G times M in this way, now it resembles a little bit M times M. The only difference is that in the middle there is a G. It's not M times M, it's M times G times M. But we can repeat what we were doing before in this new context. Let me introduce some obviously useful notation. Let's suppose I have two pairs of points in this space, xy and yz. If it happens to be the case that this element here is equal to this element here, as you see in this formula, let me just define this composition to be x, z, like that. If I define that, make this funny choice of notation, then I can simplify a little bit the definition of the multiplication of two kernels, which you still see up there. Namely, you could write it this way. You just integrate over all possible ways of factorizing gamma as gamma 1 times gamma 2, k1 of gamma 1, k2 gamma 2. And maybe it's worth to note, what is this integral? Well, it's this. If you look at the set of all pairs, gamma 1, gamma 2, such that gamma 1 is composable with gamma 2, and the result gives gamma. So if gamma is given, if x and z is given, the only way you can make a pair which is composable to this is to vary y in this way. So this funny space is just a disguised copy of m. And so when I'm doing this integration here, in effect, I'm just integrating over m. All right, now here's another construction. Maybe down here, I'll define a composition in this way. Lots of, let me call it x1, g1, x2. X3, I guess, is logical. What's a reasonable composition here? Well, this is a reasonable composition. This triple satisfies this law, assuming the other two triples do. So it's a new composition law. And so I can define in this context a composition law exactly as I did before, namely K1 of gamma 1, K2 of gamma 2. And maybe I'll stick it down here. If I look at the set of all factorizations, for a fixed gamma, if I look at the set of all factorizations, as you see in this integral, or as you see here, maybe I should say here, this is for gamma fixed. This is now, well, it's no longer a copy of M, but it's a copy of G, and G is a Lie group, so we know how to integrate on a Lie group. There is Haar measure. And so when I write this integral here, I mean that we use Haar measure. Okay, and now I've built a new algebra. I look at all functions. Maybe I should be a little careful here. To make sure the integral converges, maybe I should deal with compactly supported functions on this space. I define convolution in this way. It's well defined, and I get a new, interesting convolution algebra in this way. If you're a specialist, then the right thing to do, it's some small detail. The right thing to do is to complete this algebra into a Banach algebra. And I'll write the result as something like this. The C-star algebra of G, semi-direct product M, like that. So just for comparison, if I were to do this for the space, which was M times M, as at the very top, this would be this C-star algebra of classical C-star algebra of compact operators, as in the work of Hilbert. But now, all of a sudden, there's a huge variety of algebras to study and possibly apply to different problems. And of course, what I want to do is take this concept and return to elliptic operators. But first, let's just look at a fun example. So let the manifold be the circle. And consider the group of integers acting on a circle by rotation through some angle here of theta. So the group, I'll just choose to be this discrete group of integers. It's a Lie group. And the way the group is acting on the circle is that the integer 1 is acting by rotation by the angle theta. And it gets the most interesting when theta is an irrational multiple of one entire revolution. And so there's an algebra here which you build in this way, and which you might be relevant. It might be relevant to the dynamics of this action. It's a famous C-star algebra that people have studied for many reasons. It's called A theta, so-called irrational rotation algebra. It's one of these C-star algebras. And just to show you one thing, to tell you how interesting this is, let me make one remark about the structure of idempotence in this algebra. It's very, very interesting. First of all, to go back to the algebra studied by Hilbert, the C-star algebra of compact operators. Idempotence in here, I mean elements of the algebra E, such that E squared is equal to E. Usual elements in the sense of idempotence in the sense of algebra. So these are operators on a Hilbert space, which are idempotent operators. E squared is equal to E. And they are compact operators. It means not very big, given by kernels. All of these things are classified by their rank. Any two idempotents with the same rank are essentially the same. And the rank, of course, it's a positive number and it's integral, like that. On the other hand, if you study now this new convolution, why not? There's also a rank in this context. You can see from the result I'm about to write down that this rank is much more strange than the rank up here, because the rank takes values which are not just integral, but they're also integral multiples of theta, like that. And so it's very strange and interesting what goes on. And this algebra of integral kernels, it somehow remembers the amount of the angle of rotation. In a very strange way, it remembers the angle of rotation. This result can be captured or recaptured, can be understood using K-theory, especially the K-theory invented, the version of K-theory invented by Professor Kasparov. So it's very beautiful and interesting. The first example that you might study already is very deep and interesting. But we're going to look at, go back to this world of, we're going to go back to this world of elliptic operators here, try to solve this problem here. And we shall solve it following Connes using this construction from the left. And so now I'm going to build a family of convolution operators. Here we studied just one individual one. Here's now we study a family, which is kind of interesting. And the parameter I'll call S, and S will be a real number. So we build a family of constructions exactly like this business here. And in each member of the family, the group will be Rn. And in each member of the family, the manifold also will be Rn. So it's not compact for a moment, but okay. And now the only thing which distinguishes the families is the action. So the question is, how does a group element act on a manifold element? And there's going to be one action for each number S. Maybe I indicate the action like that with a subscript. So this is defined to be x plus, and now we just rescale usual addition, s times g. It makes sense because x and g are both vectors in Rn, and so you can form any linear combination. Okay. It's just a linear combination in a vector space. And it's interesting to study the results. So I'm interested in the C-star algebra of G, semi-direct product. Now I have to put in S somewhere so we remember. Maybe I'll put it down there. So I'm taking functions on G times M, let's say continuous compactly supported functions on G times M. I'm defining a convolution multiplication like this. And then, just as a matter of technicality, I form some completion, some closure, somehow, no big deal. Basically, I form this convolution algebra, exactly this one here. And it's very interesting what happens. There's a dichotomy between what happens when S is not 0 and when S is 0. If S is not 0, where are we? Here. If S is not 0, if we examine this space for a moment, this one up here, I said that in this space, X is determined by G and Y. But if S is not 0, G is determined by X and Y, because if S is not 0, you can compute G from X plus S times G and X, right? So G is 1 over S y minus x. I'm using this notation here. A triple in this space has the property that x and y and g are related, and the formula for the relation is what I wrote down there. So what happens is that in this particular example, when S is not 0, you can forget about G. You can forget about G. It's not actually there. You can determine G by 2 copies of M. And so what you get is just the compact operators. You're in the world of Hilbert. On the other hand, suppose S is 0. If S is 0, there's no action at all. It's actually just a trivial action. And if you think about it, this convolution multiplication is just a combination of 2 things. The convolution multiplication, as far as the variable x is concerned, is just pointwise multiplication. But as far as the group element is concerned, it's ordinary convolution of functions on Rn, like you learn about in harmonic analysis. And so, maybe I'll put an isomorphism there. I'm going to write it like this. What I'm going to do here is take Fourier transform from G times M. I'm only going to take Fourier transform in the variable G. And let me call the dual of G, maybe I should just call it G hat, like that. From this guy to this guy. And now I'm just also making the obvious identification of G times M. Remember that G in this case is Rn, so it's Rn times Rn. That's a copy of the tangent bundle. Like that. So when I vary these group actions, I obtain a family of algebras, a family of convolution multiplications, and most of the convolution multiplications are just these compact operators. So this is just Hilbert's compact operators on L2 of M. But in one special case, there's one special value, and there you get the functions on the cotangent bundle. And there's a wonderful small miracle. So we have here some type of continuous family. In C-star algebras, it's called a continuous field. So I want to think of these spaces together with multiplications. It's invariant, although we built it using lots of linear algebra, so lots of linear combinations were used to build this family of algebras. Actually, once you've built them, they don't depend on linear algebra. They only depend on the underlying manifold. So this whole thing is invariant under the group of diffeomorphisms of M. So although we defined it using manifold structure, using vector space structure, it only depends on the underlying C-infinity manifold structure. And the really marvelous theorem, it's not difficult. Due to Connes is the following. Following fact, that if you look at the morphisms of algebras from C0 of R into these C-star algebras that we've built. Now I'm going to, well, first maybe I keep this notation. Nobody actually writes this. They use some other notation here. They talk about the fiber of what's called the tangent groupoid. They write it like that. The morphisms that you get in the following way. On the one hand, we could take this von Neumann symbol from before of a rescaled version of D. Namely, I'll just multiply D by S to the Q. Q is the order of D. That's when S is not 0. And here we'll just take the usual classical or principal symbol. When S is 0. These things here, oh, here we go. Exactly, these things here, maybe I'll try and squeeze it down here, form a continuous section. Or a morphism, continuous family, I guess. Continuous family. R, a continuous family of morphisms, compatible with continuous variation. And so there's this really remarkable and unexpected way of smoothly, if you like, degenerating Hilbert's algebra of compact operators. Here we go, Hilbert's algebra of compact operators, which is, of course, highly noncommutative. It's inspired by matrices. It's noncommutative, simple algebra. Somehow it gets deformed into this algebra of functions, of course, far from simple and far from noncommutative, also very commutative. Okay. And what are we doing? The way to think about this is that this theorem links together two things. One is the classical symbol, which is easy to calculate in local coordinates. You can simply write down the principal symbol of any operator. If I give it to you explicitly, for example, I give you the Laplacian, then you can write down what is the principal symbol in a very explicit way. And so the principal symbol here is very, very computable. This von Neumann symbol is not computable at all. No longer there. The reason it's not computable is that it involves all of the eigenfunctions of the operator. To calculate what is the von Neumann symbol, you have to take the operator D and you have to solve the eigenvalue problem, df is equal to lambda f, completely. So you have a complete basis of eigenfunctions. And so it's very, very difficult to understand what is going on here when S is not 0. It's very, very complicated to understand what's going on. When S is 0, it's very easy to understand what's going on, and yet they vary continuously one to another. And one famous application, which is a very old theorem, it goes back to the beginning, the time when Hilbert proved his theorem. But it's really the first thing you can extract from this type of mathematics is Weyl's law for the asymptotics of the eigenvalues lambda j of an operator D. And what it says is that these eigenvalues behave like this, roughly speaking, some constant times j to some power, which is something like q divided by the dimension. So this numerical fact about the asymptotic behavior of eigenvalues follows just very naturally from this general fact here. Okay. And I don't have time to say more than a very little bit about this, but I think it's clear from what you see here, from our discussion of symbols and so on, that something like the following should be true. If you have an elliptic operator D, it has a symbol that we were just discussing. I'm talking about the principal symbol, the one that you can calculate. And one of the great insights of Atiyah-Singer is that the symbol of an elliptic operator defines an element in K-theory, like this. So when Atiyah-Singer proved the index theorem, their fundamental insight was that K-theory played an important role. And in particular, the symbol, the principal symbol of an operator, defines a class within the realm of cohomology theory, within the realm of K-theory, some homotopical invariant of an operator. On the other hand, there is this von Neumann symbol, and it defines a class in the K-theory of Hilbert's algebra of compact operators, like that. It's some complicated thing. I have a C-star algebra, not a space, and now I took some K-theory of it. It doesn't matter what this is. The only thing you need to know about this abelian group, so this is some cohomology group, and so is this, but this one is just equal to Z. It's not hard to calculate this thing here. And what you get here is the famous analytic index, the analytic or Fredholm index of D. So one construction somehow smoothly, continuously at least, interpolates between the analytical index that you see in the famous Atiyah-Singer index theorem and the topological index. They both live in the same world. It's not a proof of the index theorem, but it's very encouraging that you are working towards the proof of the index theorem just by making this construction. So I can't say any more about that. And let me just close by hinting at some other more recent developments using the same technology. One more piece. The first is a piece of work I admire a great deal. And it has to do with index theory, not on smooth manifolds, but on so-called contact manifolds. Well, they are particular cases of smooth manifolds. Smooth manifolds with extra structure. So a contact manifold is like an odd-dimensional symplectic manifold. And what I like about this is that the correct formulation of the index theorem. So there is an index theorem like the theorem of Atiyah-Singer for such manifolds. They're all odd-dimensional. In the world of Atiyah-Singer, there is no index theory on an odd-dimensional manifold, at least for differential operators, but here it's quite different. Now, the thing about contact manifolds, an ordinary manifold is locally diffeomorphic to Rn. That's the definition of a manifold. A contact manifold is something which is locally diffeomorphic not to Rn, but to the group of nilpotent matrices of the following sort, like this. And so what do I want to do? I want to put an x1 here, and a y1 here, and an x2 here, and a y2 here, da-da-da. I've run out of room. And zeros everywhere else. So in this particular case, I drew the example where n is equal to 2. So this is a group of matrices. It's not an abelian group. It's very close to being an abelian group. It's a step 2 nilpotent group. But it's not a abelian group. And the construction that I outlined here gives rise to a symbol class which lies in a very funny place, namely in the K-theory of what you might call the C-star algebra of the bundle of Heisenberg tangent spaces of M. And this thing here is a bundle of nilpotent groups. The tangent bundle is a bundle of a usual manifold, is a bundle of vector spaces. And each vector space, each tangent space, is the best approximation to the manifold at any given point. So in this world, the best approximation is not a vector space, it's a nilpotent group. And so using the language of Alain Connes, it's easy to understand where the symbol class should lie, the symbol class of Atiyah-Singer. And it's not in the world of ordinary topology. It's in this strange world of noncommutative K-theory. And you would not discover that. You would not even know how to formulate the index theorem. Indeed, this is exactly what happened. People struggled for 10 years to formulate the index theorem. They failed even to formulate it because they did not know where the ingredients should lie, but they follow very naturally out of this development here. I'm not going to spend time on the other thing, except to just write it down. Developments related to Bismuth's work on the hypoelliptical class. Hypoelliptic. Okay. It's time for me to stop, so thank you very much.